Hey guys, and welcome to a new video in this artificial intelligence tutorial. In this video we're going to talk about the different kind of value functions there are in reinforcement learning, and then we're going to talk about Bellman equations and how we can solve the Bellman optimality equation. So first of all, we're going to have a short recap from the last video because we're going to use some things in this video as well. So in the last video we talked about these Markov decision processes and the Markov property. So a process has Markov property if a state, like if we're in a state and we take an action, then that action only depends on the state that we're in now, and it doesn't depend on any of the previous state that we have already been in. If we need some kind of information from the previous state, like we just incorporate or like implement that information as memory in our given state. So we're in a given state, and from that given state we're taking an action, and that is a Markov decision process. And we also had this example with the robot arm and reinforcement learning, where we had this example with recycling robot that did some different kinds of things. And then we talked about the goals and rewards for an agent, like how we can set up goals and what are rewards and how can we define rewards for our agent. And then we talked about some rewards and returns and the episodic continuing task together with the discounted return. So when we're talking about continuing task, we don't have like a finite time steps. So we need to discount our returns. So the longer we come out in the future, the less impact the rewards have on the action that we're going to take in the next couple of time steps. So these are the most important things that we talked about in the last video. So first of all, we're going to talk about policy in reinforcement learning and what a policy is. So what is the probability that an agent will select a specific action from a specific state? And this is what a policy in reinforcement learning describes. So let's say we're given a specific state, and then we need to like find the probability of the next action the next specific action we're going to take. So we can talk about like a policy of a set of actions that we can take for our agent to reach its goal. And then we say in reinforcement learning that our agent, it follows a policy, so it's following a policy around, and then it's taking actions from that policy. So, and then we can have like some a policy is like a set of optimal actions to take for each step when we're following this policy with our agent. And then the policy is updated all the time when we're training our agent and it's interacting with the environment. And then we're updating the policy so we get these optimal actions in our policy, and then we can just follow our policy and we will get the most optimal policy, and then our robot or like our agent will return the maximum reward or return. So now we're going to talk about the value functions, which we're going to use as well. And the values functions, they say something about like how good is a specific action or a specific state for the agent. And then we can set up these 4 different kind of value functions here, where first of all we have like these predictions here for the state value. So for a given state, we can calculate like a value for that state, or we can also have like an action value here. So let's say that what is the value for taking this action here given a policy. So this q subscript pi here and v subscript pi here is a policy that we're following. So in this case here, when we're taking like a value state, then we calculate the value for the next action we take, and then after we've taken that action, we will just follow the policy that is given, or like the policy for the agent. Then we're just following that policy. And we're also going to talk about like the optimal value functions and optimal state values and action values, where we just try to like find an optimal solution for our value functions. So the expected values here are more like theoretical, and we can't really like use it in a practical way. So these are more like the theoretical like value functions here, and then we try to estimate those value functions here, which we can apply it in some practical examples. So this uppercase V here and uppercase Q here is the estimates of these values for these value functions here that we can actually like imply in our reinforcement learning implementation. So the first value function here that we're going to talk about is the state value function. So the state value function tells something about how good any given state is for an agent following a policy. So right now we're in a given state, and then it measures like how good that state is for an agent when we're following this policy here. And then the value of a state and then like the state value function, it is like the value of a state under a policy. So first of all, here we have this v subscript pi here, which is the policy that we're following, and then we're given some state here, and then it will be the estimated return here, g subscript t here, is the discounted return over time for a given state here that we're given in our value function here, and then we can like sum it up down here with the like more mathematical like expression. So it's just a summation of all like the discounted returns for a given state that we're in, because the state value function describes how good any state is for the agent following the policy. So this is the estimated expected return for a given state that we're in. We also have this action value function, and the action value function describes how good it is for an agent to take any given action from a given state while following the policy. So first of all, here we have this q subscript pi here. So, and then we're given a state and action value pair. So we give it a state that we're in now and an action that we're going to take, and then we try here to estimate the discounted reward, like the discounted return again, given a state and an action in this case here, because we're talking about the action value here. And then the value, and then the action value function is a value of an action under the policy. So we take an action in our action value method here, and then after we're taking that action, we're just following the policy further on. So we can also talk about this as the Q function, which is the quality of taking an action in a state. So we're going to talk a lot more about the Q function and Q learning in some of the upcoming videos, because it's a real nice thing, and it's probably like one of the most like implemented functions in practical examples, where we have this Q function here given from the action value function, which is like it estimates or like it measures how good an action is under a policy. So we can also talk about the optimal policy, as I showed you on with some of the value functions here. So an optimal policy is like, when we're having this optimal policy, the goal for reinforcement learning algorithms is to find a policy that gives the agent a lot of rewards if it follows the policy that it's given. And then the optimal goal for like optimal policies is to find a policy that gives more return than any other policy. So when we're training our agent in the environment, we're finding out a policy all the time, and we're updating that policy over time when we're interacting with the environment. And then our optimal goal is to find that policy that just beats any other policy and gives the most return possible. So this is like an optimal policy, and we're going to talk more about that as well. So we also have these optimal value functions here, where we have the optimal state value function and the optimal action value function. So first of all, the optimal state value function here is like the highest expected return possible for any policy for each state. So we can set it up mathematically like this here, where we have this v subscript star here. So we use this subscript star here when we're talking about some optimal value functions. So again, we're given a state here for the state value functions, and then we take the maximum value of like the maximum value for our state value here. And then we can also talk about optimal action value function, and we have this optimal Q function here, which we're also going to talk about a lot more and going more in depth with it in the upcoming videos. But the optimal action value function is the highest expected return possible for any policy for each possible state action pairs. So when we're talking about action value, the function, we're given a state action pair here, and then we just take the maximum value of that, and we try to like find this optimal action value function, which is like the highest expected return possible for any of the policies for each possible state action pair that we give. So to have an overview here over like the different kind of value functions that we've been over, like this is just to give you an overview where we have these 4 different kind of value functions, the two predictive value functions, and then the 2 optimal value functions, where we have these state value function and the state action pair value function, and then the optimal value function and the optimal state value action value function down here. So these are just the equations that we've already been over on the previous slides, but just to give you an overview over the different kind of equations here. So now we're going to talk about the Bellman optimality equation, where like the goal is to solve the Bellman optimality equation, and the optimal action value function must satisfy the Bellman equation when we're trying to solve it. So the optimal, the Bellman optimal equation is the equation here to the left, and then our action value function to the left here, where we're given a state action pair. So this is the Q value. It must satisfy, or it must be equal to the Bellman equation here on the right. So the Bellman equation here is the respected return for the next state, and then the discounted returns, or like the discounted action value function for the next state and the next action that we're taking. So the expected return here from starting in a state, selecting an action, and following the optimal policy after that. So we have talked about this, where we're first taking an action, and then we have the reward here for that action that we're taking, and then we're just following our policy after that, and then we can calculate the discounted return here and sum them together, and that will be the expected return here for our optimal action value function. So the expected reward for the action plus the max expected discount return possible for any next state action pair for our example. So ultimately, we're trying to solve this Bellman optimality equation when we're dealing with it in reinforcement learning. So when we're trying to solve this Bellman equation here, we're finding an optimal policy by solving this equation, and it requires some different kind of stuff, like for example, like accurate knowledge of the environment dynamics. So we need to know the environment dynamics very accurately to be able to solve our Bellman optimality equation, and also to find the optimal policy. Because in reinforcement learning, we want to find the optimal policy. So we take like the best path, or like the best set of actions to take to reach our goal for the agent. And we also need to have like enough space and time to do the computation. So we're going to talk about that as well. And the markup property, we also need the markup property to be able to find this optimal policy in reinforcement learning. So how much space and time do we need? Because I just mentioned that we need we require that we have enough space and time to do the computation to like find the optimal policy. And let's talk about like we can have this polynomial in number of states. So and the number of states is often huge in some like reinforcement learning applications. So let's just say we're trying to implement an agent or reinforcement learning in the Go game here. Then the Go game has about like 10 to the power of 170 states, and chess as well has like number of states of 10 to the power of 47. So it's a lot of states, and it will just require too much space and time, and we won't have that in like a practical example. So we can just find an optimal policy by solving this Bellman equation when we have so many states for our game. We could maybe do it with if we were only playing like tic-tac-toe, or only had like a couple of cells or pixels in a grid. So instead, when we're trying to solve this Bellman optimality equation, we try to approximate it instead. So many reinforcement learning methods is actually like just trying to approximately solving the Bellman optimal equation, and not like having an exact solution, but trying to approximate it and get as close as possible to the optimal solution and the optimal policy by learning and like training the agent in the environment. So an example here of optimal policy here is that we have some agent here that can take some actions here, and then it will get some rewards for the action it takes. So when we're talking about the optimal policy here, and we have these discounted returns here, then when we have a gamma equal to 0 here, then we only care about the reward that we get in the next state. So in the case here, if we want to find our optimal policy for the gamma being equal to 0 here, we will of course take the left turn here, because then we will get an expected return here of 1. And if we took the right path here, we will get a expected return of 0. So the optimal policy in this case here, if we have gamma equal to 0, it will be taking the left path here, even though the expected return here for the second action will return an expected value of 2. So we can instead here take like the gamma here, set it equal to 0.9. So we have to like find some kind of balance between setting our gamma when we're trying to find the optimal policy when we're training our reinforcement agent. So in this case here, when we have gamma equals to 0.9, then we also care about the future rewards. So in this case here, if we're taking the left turn here, we can see that we will still get 1 here, and we will get 1 here for the next. But but now we have this gamma equal to 0.9, and we now care about the next step here. So actually, when we have gamma equal to 0.9 and 0.5, then we will actually like get 1.8 here for the expected return for taking a right path. So in case here that we have gamma equal to 0.9 and 0.5, then we will actually like take the right path here for this 0.9. And if we want 0.5, it doesn't really matter which path we will take, because then the expected return would be 1 for either cases. But this is just to show you like there's a lot of different kind of examples on the situations of finding the optimal policy, and it's really like a trade-off, and it's just like trying to tune these parameters and find a good balance when you're trying to find your optimal policy that your agent is going to follow. So yeah, it can be really hard to find the real gamma and find the optimal policy, and it's also why the agent has to learn over so many iterations to like try to estimate and try to find this optimal policy to be able to take the right action for each state that it's in. So when we're talking about reinforcement learning, we also have these iterative methods where the iterative methods or algorithms, it tries to converge to the optimal value or an optimal policy under some conditions. As we just talked about in the example here, where we try to find the optimal policy, so we take the optimal actions every time we are in a state. So the value iteration here, it learns the values for all the states, and then we can act accordingly to the gradient for the values of all those states here. And we can also have something called policy iteration. So these iterative methods is that like we're iterating through our environment, and we're trying to like learn the values for all the states, which can be really like really heavy for the computational when we have like a really large grid or a really large like environment. And we can also have this policy iteration here, where our policy learning incrementally looks at the current values and extract a new policy. And then we can do something called policy evaluation, where we're evaluating our policy and sees if we have to update our policy. Because the action space is finite, it might converge faster than the value iteration. So we're trying to converge as fast as possible to the optimal value and the policy, because then we have found like the faster we converge to optimal value or like policy, then the faster like our agent just learns, and the faster we find an optimal solution that we can just deploy to our reinforcement learning agent, and then it can just follow that policy and achieve its goal as fast as possible. So down here is like a timeline of how we can do this policy iteration here. So first of all, we have some initial policy here, and then here we're evaluating that policy when we're doing the training on our reinforcement learning agent. And then we get a new value here, for our policy that we're following. And then here we're iterating over our policy again, and then we'll get a new policy, or like we're updating our policy here. And then we get a new policy, we evaluate it, we have a new value function, or like a value here for the action that we're going to take, and then following the policy after. And then we're updating and changing the policy again, and then evaluating the policy, and then we can do so on and so forth, until we hit the optimal value, or we converge towards the optimal value when we're trying to approximate it. So here, just like the mathematical equation set up here for the policy iteration and value iteration. So for policy iteration, it may be slow, since each iteration requires a policy iteration. So as I just showed you in the timeline, we have to iterate through all like the policy evaluations, and then update our policy, and then do the thing over and over again when we're iterating. Where in the value iteration, we can actually we can combine the policy evaluation with policy improvement, and then sometimes we can find the optimal policy faster. So these are just like the mathematical expressions that are set up to try to find the optimal find the optimal values for a reinforcement learning agent. So to summarize what we've been over in this video here, we're talking about the value functions, the 4 different kind of value functions over here to the right, where we have these predictions for the state values and the action values, and then the optimal state values and optimal values here that we're trying to estimate by solving the Bellman optimality equation, and then we can try to converge or find the optimal policy that we can then deploy to a reinforcement learning agent, and then the reinforcement learning agent will just follow that policy and it will try to reach the goal as fast as possible. So we also talked about like the optimal policy example, where we had this gamma that we changed, and then we tried to find the optimal, in a really simple example, we tried to find the optimal, find the optimal policy for some different kind of gamma values. And then we talked about the policy iteration and value iterations for some methods on how we can try to solve the Bellman optimality equation and try to converge towards the true or the optimal policy. So thank you guys for watching this video, and remember to hit the subscribe button and bell notifications on the video, and also like this video if you like the content and you want more of it in the future. I'm currently also doing a computer vision tutorial in C++ and OpenCV, and an algorithm data structure tutorial as well, algorithm data structure tutorial as well. So if you're interested in one of those, I'll link to one of them up here, or else I'll just see you in the next video, guys. Bye for now.